On this slide, we set up the general problem. Characterize the one-step conditional law of the extreme shape tomorrow, namely, the distribution of x1 given the recent past shapes x1 minus p plus q to 1, xn minus 1. The key technical tool is a linear recurrence satisfied by the two-sided moving average coefficients, Cn, implied by the MARPQ polynomial. Rather than manipulating Cn directly, we focus on the ratios Cn plus 1, Cen, because x01 is exactly such a ratio evaluated at the random epicenter n. The recurrence shows that, away from a boundary index, each ratio Cn plus 1, 1, Cn is a deterministic function of a finite number of previous ratios. There is a special boundary case at n equals q1 where the recurrence includes an additional unit term. This is the analog of the switch event in MAR 1.1. Intuitively, this boundary is where the epicenter sits exactly at the interface between the non-causal and causal sides, and that is precisely where probabilistic branching in the next step extreme behavior can arise. This slide turns the coefficient recurrence into a statement about the support and structure of the conditional law of x01. First, the joint vector of x can only take values generated by a specific epicenter n. It equals a block of coefficient ratios around n. So, observing the past shape vector restricts the set of compatible epicenters. Second, the slide gives a key implication formula. x1 can be written as a linear function of the past shapes plus an extra term multiplied by the indicator of the boundary event n equals q minus 1. In words, if the observed past shape vector corresponds to an interior epicenter, then tomorrow's shape is uniquely determined by the recurrence, hence deterministic. Only when the past shape vector is compatible with the boundary configuration does the remaining uncertainty collapse to a single binary question. Is the epicenter exactly at the boundary or just on the interior side? Therefore, the whole conditional distribution problem reduces to the conditional probability of that boundary indicator given the past extreme shape. Here, we get the main qualitative dichotomy, Dirac versus Bernoulli. If conditional on the observed past shape vector, the boundary indicator is almost surely equal to 0 or almost surely equal to 1, then x1 is almost surely a constant. In that case, the conditional distribution of x1 given the past is a Dirac mass. There is no branching, and the next step extreme shape is fully identified by the past extreme shape. If instead, the boundary indicator is not degenerate, meaning that the same past shape vector can arise from two different epicenter configurations, one at the boundary and one not, then x1 given the past becomes a two-point mixture. Concretely, the conditional law is Bernoulli. With one probability, you get the interior value implied by the recurrence, and with the complementary probability, you get the boundary corrected value. This is exactly the mechanism that creates two competing one-step scenarios after an extreme observation. A continuation branch versus a reversal branch, both consistent with the same observed past normalized pattern. We now move from the spectral object x1 to the original time series. The goal is to approximate the one-step predictive distribution of yt plus 1 or of the one-step ratio rt plus 1, conditional on today being extreme. The logic is, first obtain the conditional law of the one-step spectral shape x1, then translate it into a predictive law for ratios and levels in the extreme regime. The next slides formalize this through the transition density of a MAR PQ and a simple large sum lemma that converts continuous conditional densities into Bernoulli-type limits. This slide provides the transition density representation for a MAR PQ written in a way that separates the innovation density from a factor involving the pure components. The main takeaway is conceptual. The conditional density of yt plus 1 given the state can be factorized into the density of a new shock term after applying the combined filter times a ratio of joint densities of the causal component sequence across two adjacent blocks. In extreme conditioning, one factor dominates, and the SBJ principle implies that the dominant contribution comes from a single large term in a sum of two independent heavy-tailed quantities. This is why the next lemma is formulated for a generic pair, Z1, Z2, with equivalent regularly varying densities. It captures the universal asymptotic behavior of the share R equals Z1 over z1 to z2, given a large total S equals z1 to z2. This lemma is the technical workhorse behind discrete predictive limits. Consider two independent heavy-tailed variables, z1 and z2, whose densities are regularly varying with the same tail index and asymptotically equivalent up to a constant factor x. Look at their sum S equals z1 plus z2 and the share R equals z1 divided by S. The lemma says that, conditional on S being very large, the distribution of R converges to a Bernoulli distribution. With probability P, essentially all the large sum comes from z1, so R is approximately 1, and with the complementary probability, it comes from z2, so R is approximately 0. This is a precise one big jump statement. When a sum is extreme, typically one term is extreme and the other is negligible. In our context, z1 and z2 correspond to two competing contributions to the next step dynamics, one associated with the causal side and one with the non-causal side. So the lemma converts a complicated conditional density into a binary selection, yielding tractable two-point extreme forecasts. This proposition applies the lemma to MAR 1.1 and delivers a sharp forecasting statement in extremes, condition on yt being very large and positive. Then the one-step ratio RT plus 1 has an asymptotic two-point distribution. It concentrates either on the causal multiplier phi or on the non-causal inverse multiplier psi minus 1. The associated weights are explicit and depend on the tail index alpha and on the relative masses of the coefficient tails. The slide summarizes them through a single parameter zeta. Intuitively, the branch RT-plon pecai corresponds to the case where the epicenter sits on the causal side or at the switch, so tomorrow behaves like a standard AR step. The branch RT plus 1 equals approximately psi minus 1 corresponds to an epicenter on the non-causal side, so the extreme today is linked to a dominant shock located in the future, producing an apparent explosive ratio. The proposition also extends to two steps. The pair, yt plus 1 divided by yt plus 2 divided by yt, converges to a discrete law with three scenarios, matching whether the switch happens before or after the first step. To make the discrete limit result tangible, this slide considers a fully tractable case, Cauchy innovations in MAR 1.1. Then, we can write an explicit conditional density for the next step ratio RT plus 1, given that yt equals a large value y, and the current ratio RT is fixed at R. You should not read the formula aloud, the message is qualitative. For large y, the predictive density is bimodal, with two peaks corresponding to the two asymptotic branches. One mode is near the causal multiplier phi, reflecting the standard AR-type move. The other mode is near a shifted location involving psi1, and its exact position depends on R. This is the non-causal branch, where the extreme today is linked to a dominant shock located in the future. The two panels illustrate this with yt equals 100 and R equals 2 versus R equals 1. In both cases, the bimodality is clear, but the non-causal mode shifts with R, while the causal mode stays anchored at phi. As he increases, the density concentrates around these 2 points, matching the discrete extreme limit prediction. To make the discrete limit result tangible, this slide considers a fully tractable case, Cauchy innovations in MAR 1.1. Then we can write an explicit conditional density for the next step ratio, RT plus 1, given that yt equals a large value y and the current ratio RT is fixed at R. You should not read the formula aloud. The message is qualitative. For large y, the predictive density is bimodal, with two peaks corresponding to the two asymptotic branches. One mode is near the causal multiplier phi, reflecting the standard AR-type move. The other mode is near a shifted location involving psi1, and its exact position depends on R. This is the non-causal branch, where the extreme today is linked to a dominant shock located in the future. The two panels illustrate this with yt equals 100 and R equals 2 versus R equals 1. In both cases, the bimodality is clear, but the non-causal mode shifts with R, while the causal mode stays anchored at phi. As V increases, the density concentrates around these 2 points, matching the discrete extreme limit prediction. We now move from theory to a practical diagnostic. The idea is to estimate a MAR model, compute innovations under both the causal and the non-causal representations, and then look at how extremes line up in the resulting residual series. The next two slides explain what we should see in an ideal pure causal versus pure non-causal case, and why mixed models typically produce a characteristic asymmetric pattern. This slide is about a simple but powerful diagnostic. Residual plots computed under the wrong direction typically reveal structure in extremes. In a purely causal model, large observations are generated by large past shocks. So, if we compute causal residuals, extremes in the series should correspond to extremes in the causal innovations. Extreme points align cleanly, and the residual plot looks roughly symmetric with no systematic lead-lag pattern. But if we instead force a non-causal representation onto a truly causal series, the implied non-causal residuals will display dependence patterns around extremes. The model tries to attribute today's extreme to future shocks, which creates visible clustering or systematic slopes in the residual scatter. Conversely, in a purely non-causal model, extremes are linked to future innovations. Non-causal residuals align with extremes, while causal residuals reveal artifacts. So, operationally, you compute both sets of residuals and check which representation makes extremes look most IID-like. This is exactly aligned with the tail process view. In the correct direction, the epicenter mechanism is consistent with IID innovations. In the wrong direction, the model compensates and leaves an extremal footprint in residual space. On this slide, we illustrate the diagnostic on real data. Corn futures prices fitted with a MAR 1.1. The first panel shows the price trajectory and highlights a pronounced bubble-type episode from July 2, 2018 to February 3, 2020. The point of the example is not to claim a structural bubble model, but to show that a stationary, mixed causal-noncausal specification can reproduce the asymmetric run-up and correction patterns that appear in the data. In the second panel, we plot the normalized residual components around an extreme date. The red dashed curve is the non-causal residual, the black solid curve is the causal residual. Following the reading rule from the previous slide, when one component stays close to zero on one side of the window while the other dominates, it signals which regime is active and where the switch occurs. Here, the asymmetry between the two curves already suggests a mixed mechanism rather than a purely causal or purely non-causal fit. This slide zooms in on the residual plots using the absolute normalized magnitudes of the estimated non-causal component and the estimated causal component for horizons h from -30 to 30. Three reference dates are selected: t equals 210, t equals 240, and t equals 350, interpreted respectively as before the peak, around the peak, and after the peak of the episode. The key message is the inferred switch location, hence an implied epicenter index n and a turning point timing. Before the peak, t equals 210, the switch is far to the right of the window, consistent with an epicenter around n is approximately equal to -30. The non-causal component dominates over many positive horizons, matching a continuation phase. Around the peak, t equals 240, the switch is close to the center, consistent with n approximately equal to 0. This is the boundary configuration where the theory predicts the strongest uncertainty between continuation and reversal. After the peak, t equals 350, the switch is far to the left, consistent with n approximately equals 80. The causal side dominates, matching the post-peak unwind and a return to past-driven dynamics. Let me conclude with what the spectral tail process view delivers for MAR models. First, it provides a structural explanation of bubble and crash patterns within strictly stationary, heavy-tailed dynamics. An extreme episode is driven by one dominant innovation, and the linear filter propagates it into a quasi-deterministic path. Second, it gives a discrete representation of extreme shapes via the epicenter index n, which makes extremal trajectories interpretable and classifiable. Third, it yields tractable approximations for key conditional laws. The one-step spectral shape x1 given recent past shapes, and the one-step predictive law of yt plus 1 given that yt is extreme, often reducing to Dirac or Bernoulli mixtures, especially in boundary cases like MAR 1.1. On the applied side, the causal-noncausal residual plots provide a diagnostic to distinguish pure causal from pure non-causal dynamics, and to reveal mixture behavior in real data. As open directions, multivariate extensions raise questions about conditioning sets, heterogeneous tail indices, and co-movements of extreme episodes, and we also need robustness analysis under misspecification and estimation error. For instance, confidence bands for residual diagnostics and stability of the inferred branch probabilities